Chapter 3, Day 6, Curve Sketching Part 1. I will post a Part 2 to this. First, I'm going to focus specifically on the graphs that I gave to you in the packet, numbers 61 to 64. So looking at the graph of a function, what are some characteristics that we can be able to determine? We can identify the domain and range, x and y intercepts of the function, vertical and horizontal asymptotes, other discontinuities, and then we can also determine intervals of increasing, decreasing, extrema, concavity, and we can at least attempt to identify where points of inflection occur. On Part 2, I will focus more specifically on these attributes. For numbers 61 to 64, let's look at what the first and second derivatives tell us about the function, and therefore what the function tells us about the first and second derivatives. So we looked at this briefly in class, and we said, looking at a graph of a function, we can determine intervals of concavity, so where the function is concave up and concave down. And that's just very simply looking for an upward facing parabola or a downward facing parabola. How do we determine intervals of concavity from the second derivative? The second derivative is positive, the function's concave up, negative second derivative, concave down function, and then back to positive. And so what we discussed, and these should all be lined up. So what we looked at in class the other day, if the function is concave up, it has a positive second derivative. Well, the second derivative is a rate of change of the first derivative. So if the rate of change of a function is positive, what does it tell us about that function? It tells us where that function's increasing. So a negative rate of change would mean the function is decreasing, and then positive rate of change, again, function would be increasing. So it doesn't matter how we identify it, f prime, f double prime, or just f, we can still use the same characteristics to identify behavior of the derivative. So where does a function switch concavity? At a point of inflection. Where does a function change direction? At relative maxes and mins. So the point of inflection on the graph of the function will become relative extrema on the graph of the derivative. Okay, change in direction from increasing to decreasing would be a relative maximum. A change in direction from decreasing to increasing would be a relative minimum. Okay, now how's that related to the second derivative? Any change in sign from positive to negative graphically is a zero on the graph of the function. So for the four graphs that I gave you, they were all the graph of an original function, and you have to determine how to graph the first and second derivatives. This will be one relationship that we look at in order to sketch what the derivative graphs would look like. Okay, what other characteristic can we determine just looking at the graph of a function? We can determine intervals of increasing and decreasing. So where the function is increasing, how's that related to the first derivative? First derivative is positive. Second derivative, or first derivative is negative, tells us where the function's decreasing. And then a positive derivative tells us where the function is increasing again. So how are these points related? A relative maximum is a change in direction from increasing to decreasing. A relative minimum would occur in a change in direction from decreasing to increasing. So how do these values correspond to the graph of the derivative? Again, any change in sign is represented graphically by a zero. So relative extrema on the graph of the function becomes zeros on the graph of the derivative. So as I'm doing the next 4 graphs, refer to these 2 relationships. The first relationship, concavity of the function, and what that tells us about the first and therefore second derivative, increasing and decreasing intervals of the function, and how that's related to the first derivative. Okay, so for this one, the function here is strictly increasing. So what does that tell us about the derivative? The derivative is always positive. If we talk about concavity, there's no concavity of this function. Again, concavity in its simplest form would look like parabolas. Well, this graph obviously is an oblique line. So what does that tell us about the second derivative? The second derivative will just be 0. Okay. Positive first derivative. Where's the positive region? Above the x-axis. So, very simply, this would be the graph of f prime. Second derivative is equal to 0. Where is y is equal to 0? That's through the x-axis. So that horizontal line would be the graph of the second derivative. Now, a linear function is an easy one to represent with an equation, because all linear functions have the same equation, mx plus b. Well, what's the derivative of any line? That's just the slope of the line. Now, because this is drawn to scale, we can determine that the slope of the function given in the graph is 1. That's why the derivative graph is a horizontal line through 1. What's the second derivative of any linear function? 0. The rate of change of the slope is 0. So graphically, where would 0 be? A horizontal line through the x-axis. Number 2, and I'm sorry, this is missing. So as the directions say, graph f, f prime, and f double prime. Well, the graph of f is already given, so we don't have to do anything more. All right, let's look at this function. This function starts out decreasing. We always trace graphs left to right. So my pencil would be coming down until 1, and then after 1, the pencil goes back up, so the function would be increasing. What does that tell us about the derivative? The derivative is negative before 1 and positive after 1. Now let's look at concavity. This function is always concave up. Concave up means the second derivative is strictly positive, which means the first derivative is strictly increasing. So no points of inflection. So now let's put the characteristics of the first derivative together. First derivative is increasing, meaning our pencil has to always head in the up direction, and our first derivative switches sign at 1. Relative extrema on the graph of the function become x-intercepts on the graph of the derivative. Negative region is below the x-axis, positive region is above the x-axis, and my pencil's headed up the entire domain. So that oblique line would be the graph of the first derivative. The only thing we know about the second derivative is that it's positive, and the second derivative is the rate of change of the first derivative. Well, we just talked about this. What's the rate of change of a line? It's just the slope of that line. So the line I drew in blue has a positive slope. So the second derivative just needs to be graphed in the positive region, which is above the x-axis. Now again, without the equation of a function, we can't determine the exact points or the exact slope. All we know are the points that we can estimate and approximate from the graph of the original function. So these are just sketches. Just based on this information, what would the derivative and the second derivative graphs look like? Okay, what's the behavior of the function? My function starts to increase, so pencil headed up, we'll say until about here. We'll call that negative 0.1. Pencil headed down until about here. We'll call that 1.5. So the function's decreasing. And then after 1.5, our pencil's headed up again. So that tells us that the first derivative is positive, then it switches to negative, then it switches to positive again. Now let's look at concavity. Function is concave down, we'll say until about 0.5. And then the concavity switches to concave up. So this tells us on the first derivative starts out increasing, then switches to decreasing after 0.5. So the second derivative is positive to the left of 0.5 and negative to the right of 0.5. So let's look at the characteristics of the first derivative. Relative extrema on the function becomes zeros on the graph of the first derivative. So we have zeros here. Points of inflection on the function become relative extrema on the graph of the derivative. So at 0.5, we're going to have a relative, I messed this up. Concave down, decreasing to the left of 0.5, increasing to the right of 0.5, negative to the left of 0.5, positive to the right of 0.5. Sorry about that, guys. So at 0.5, we're going to have a relative minimum. I will sound like a broken record again. Without a function, we can't determine what the y value of the mins, maxes, points of inflection are. We can only estimate what they are. Points of inflection become turning points on the graph of the derivative. I know it's a relative minimum, so it's going to be smaller. The y value will be smaller than the x-intercepts. First derivative is positive, then negative, then positive. Positive is above the x-axis, negative is below the x-axis, positive would be above the x-axis again. F prime, my pencil will start out coming down, so decreasing until 0.5, increasing after, and then we can verify that this portion of the derivative graph is above the x-axis, then below and above the x-axis again. Now looking at the second derivative, all we know about the second derivative is that there's an x-intercept at 0.5. The second derivative switches from negative to positive, so from below the x-axis to above the x-axis. And if we look at the first derivative being parabolic in shape, we know the rate of change of any quadratic is a line. So it verifies that the second derivative is sketched correctly. Okay, this one's a little bit trickier. Vertical asymptote at 2 means f of 2, f prime of 2, and f double prime of 2 do not exist. So that vertical asymptote will be constant on the graph of the first and second derivatives as well. So my function pencil's heading up, increasing before 2, decreasing after 2. So that tells us that the derivative will be positive, then negative, above the x-axis before 2, below the x-axis after 2. Now when we look at concavity, I'm going to keep 2 on the number line because it's a discontinuity. To the left of 2, my function is concave up, and to the right of 2, my function is also concave up. And again, I'm keeping that discontinuity on the number line. So that tells us our derivative is strictly increasing, which tells us our second derivative will always be positive, will always be above the x-axis. First derivative is above the x-axis, and I'm increasing at the same time. Above the x-axis, increasing